All right, so looks everything's okay now.
And the copy is back.
Oh, that's okay. Yes.
There's no actual credit for this point. It's my copy.
So let's start. So today I would like to introduce our second lecture of RA-seq data analysis. So let's just go from what I talked about last time. Last time I showed you actually one slide about the recently updated experimental parameters of RA-seq data experiment. So currently, this data is just got it yesterday from the Dr. Hongyu Gao at the CMG, School of Medicine, the Center for Medical Genomics. So basically, currently there are 4+1 protocols used to generate the RA-seq data currently used at CMG. So the first one is the regular mRNA sequencing, and the sample demand is more than 100 nanogram of mRNA. Second is ultra low mRNA sequencing. They can also do the experiment on ultra low amount of input sample. So the requirement is more than 200 picogram. And the third. This one. Okay, cool. This one and just put it here. And then put this on the bell. Great. Okay. Yeah. So the second one is about it's ultra low mRNA sequencing, and the third one is the regular total RNA sequencing, and it's the same requirement, sample amount requirement as the regular mRNA sequencing. And fourth one is the ultra low total RNA sequencing. Currently, they require more than 500 picogram of our total RNA input sample. I mentioned the +1 is there's another technique, new technique named single cell RNA-seq data, single cell RNA-seq sequencing. So I will introduce the details about this part in my next lecture. But the protocol to get the single cell RNA is different from the four regular protocol. Basically, they may need one flow. It's kind of one step in the pipeline. Namely C1 fluidine. Use this machine and use the pipeline to extract the cDNA from a single cell. And the input here, the current input demand is 0.0 nanogram cDNA sample per cell, and these are the same. Yeah. So before I start the alternative splicing part, I would like to revisit the differential expression test by DE-seq2, which I have introduced at the end of last lecture. So first, I would like to talk about one thing I didn't mention a lot is about statistical power. So in plain English, the statistical power is the likelihood that a study will detect an effect when there is an effect to be detected. So that means the probability to reject H0 when the truth is H1, the alternative hypothesis. So basically, what we want to the reason we want to use DE-seq2 is just to increase the statistical power. So, but there are several ways to increase statistical power, but one way here we are using is the major way we are using is introduce prior knowledge of data distribution, so which can largely increase the statistical power. So here, but I mean, here I would like to use one example to show how can we increase the statistical power by using the prior knowledge. But here, please always keep in mind the prior knowledge of data distribution need to be rational. So here is actually this four figures shows first this figure in the left top shows the data. I have simulated two data. The first one is 100 data from one gamma distribution. The second one is another 100 samples from another 1,000 samples from 1,000 random samples from one gamma distribution. The second one is from another gamma distribution. And this is a histogram of the two simulations. So actually, the two simulations, actually the parameters I used to simulate these two different random random observations are different. So you can see the distribution. They can just kind of recover the distribution for the parameters of the gamma distribution. So for each of the data, for this data, if this is a real case, we got this observation, but we don't know the underlying what the distribution, the true distribution behind it. We can have different assumptions. First, we can assume like this data are from the negative binomial distribution. And to fit the negative binomial distribution, if we know it is from negative binomial distribution, we know the shape. And to fit it, what we need, we just need to recover the two, or estimate the two parameters in negative binomial distribution. So it can be it can be either gamma and R, P and R, what we used for the the probability of the success and the number of success before the end, before the end. And also we can use mean and the variance. Actually, we can derive just one side from the other. So basically, with this observation, we can, if we use mean and variance, we can compute the mean of the observed data of the first simulation of the first data set, and also the variance of this one, and also the mean of the second one, and the variance of the second one. And then we can fit it. And then it's kind of okay. We get this, and with the assumption of negative binomial distribution, and kind of get the distribution. We fit the distribution to the data. And then if this data is truly negative binomial distribution, what we do is we use the parameters and the negative binomial distribution to simulate 1,000 samples from the first distribution and the 1,000 samples from the second distribution. And then we plot the histogram. And then we can say, okay, this one is quite similar to this one. So negative binomial, even though this is original from gamma, but the negative binomial distribution at least has recovered the shape and with a good fitting, kind of with a good fitting. And the reason is that, like I mentioned last time, is negative binomial is actually a Gaussian Poisson distribution with a prior, with the lambda. With the lambda, it's not a fixed number, but with a prior of gamma distribution. So definitely it can be recovered by this case. The gamma distribution can be recovered by the negative binomial distribution. But if we change our assumption, to the data. We don't know what's the true distribution of the data with the observation. We assume, okay, this data made from the Gaussian distribution or normal distribution. We still compute the mean and the variance. And with the assumption of Gaussian, we can still just recover the distribution of just recover to Gaussian distribution of this data. And when we simulate it, and then we still generate random numbers from these two distributions, and we say this is the result. So we can see this shape is totally different to this shape. What we can say here is that the Gaussian distribution is not a correct, just a rational assumption of this data, the distribution of this data. But think about if we want to test the differential expression test. This is one condition, this is one condition. And if we assume Gaussian, we will see these two distributions are totally different and with no intersection. So what we get here is if we just use Gaussian assumption and do the t-test, the differential expression significance will be very high. It should be much higher than this one, just by probability. And also the third assumption we have is uniform distribution. We just get this data, obviously it's not uniform, but they still use uniform assumption. And we just use MLE to fit uniform distribution and get the simulation from it, just get the random variable from the fitted distribution. And we use uniform distribution assumption. And our test will be, if we use uniform distribution and then we use the fitted distribution and then to do the test, the difference between the two distributions will be smaller. But what I want to say here is that if we introduce the prior knowledge about the data distribution as Gaussian distribution, we will really largely increase the power. Even though it is not significant, we can identify significant. But for some cases, but for some cases, it's significant, but cannot be identified by the gamma distribution assumption or non-negative binomial distribution assumption. It can be identified by Gaussian, but it may also give you a lot of false discoveries. But here, but also if we use a uniform distribution as the assumption, we cannot get, even though this is significant, but we use some test. If with the underlying assumption, with a lot of assumption about the uniform distribution, the result will be non-significant. So kind of a similar understanding is like the Mann-Whitney test we have introduced before. So if you go back to search about Mann-Whitney test, it's used just a rank to test the two different groups of variables, two different groups of observations. So just for example, for 3 to 3. So for 3 to 3, if this the 3 to 3 is like located is the first three observations like just 0.1 watt, and the second three samples are all 100 watt. If you use t-test, it will be extremely significant. But you use rank test, what you have is just the first one is the first three are just rank 1, rank 2, rank 3, and the second group is rank 4, rank 5, rank 6. This is what you the most information you can get. And the statistical significance will be much lower comparing to the t-test to the Gaussian based to the test with the prior assumption of Gaussian distribution. So here with this figure, I just want you to keep in mind that we may use the prior knowledge of data distribution to increase the statistical power. But if the prior distribution is wrongly introduced here, it's just wrongly assumed, it will cause some it will cause some problem. Definitely for this case, it will cause false discovery. But for this case, you may cause like the statistical power is too low because the distribution is not is incorrectly assumed. And also how to get a rational distribution.
So if we go back, so all these distributions are you plotted. This is for one specific gene across multiple samples. Is that correct?
Yeah.
So what you are trying to
exactly.
So it's not like one sample, the distribution of
all the genes. No, this is just a simulation. It's just,
okay.
Yeah.
So but you're trying to simulate for one specific gene across maybe 100 people.
Yeah, 100 people or 1,000 people, and for two conditions, like 1,000 healthy people, 1,000 people with disease, like that. Yeah. And also here is. Sometimes there are some ways to get a rational distribution. First, as I mentioned, the simulation-based study and goodness of fitting test. So if you after you get this data, there are some tests. There is a test namely goodness of fitting. So you can just after you fit this data with this distribution, or you can directly, without fitting, you can directly test if this data forms Gaussian for Gaussian or normal distribution. And also, sometimes we can get from biochemistry or system biology theory. So it's like this case for the DE-seq2. We get the RNA-seq response distribution like we'll talk about. It's like, first we talk about the binomial distribution. Like get some case, just with k number of cases out of n experiment. And also we talk about the p is very low and the n is increased is very large. It can be approximated by a Poisson distribution. And then we talk about the Poisson distribution sometimes doesn't work because when we empirically found that for Poisson distribution, the mean needs to be equal to variance. But actually in the real data case, we found the mean of the real data doesn't equal to the variance. So this is I will show this figure later in the hands-on part. So this is from the real data case. So of the real counts through one experiment with 6 samples. And what I did here is that just for each of the gene, I compute the mean of the gene and I compute the variance of the gene, and I use the mean of the gene divided by the variance of the gene. If this is truly Poisson, this will be centered with 1, and this value is I take log, so this will be centered at 0. But here, this is the distribution you have. 0 is here. So you can see most of the values, those are like 20,000 or more genes I have from the data, or the data of contents. So most of the genes are for this value are with negative value. So that means the data for most of the genes, the mean of the gene is much smaller compared to the variance of the gene through the 6 samples. This is common in the RNA-seq data case. And this is, and also well notice the negative binomial distribution. One requirement of negative binomial distribution is the mean smaller than the variance. This is the term. And for this case, we can say most of the RNA-seq data cases works for this one. Yeah.
Or you're saying variance is larger than mean.
Yeah, variance is larger than mean.
It's different because when you say variance is larger than mean, that means that if we use Poisson distribution, assuming they are equal, that is underestimating the variance.
Yeah,
that's the major point.
Yeah, this is the major point I will talk. Yeah, exactly. So, but I will show this how can you get this plot from the hands-on part later. And also, and the underlying model is that in the negative binomial distribution is that still for each gene, each sample, in that sample, it follows a Poisson distribution with a variable, with a lambda, we don't know. But the samples can be, there are multiple samples of one condition, but for different sample, even for the same condition, the lambda can be different. It's lambda ig. I is the gene ID, J is the sample ID. Gene index and sample index. And the lambda ig here is that the assumption in DEC2 is that the lambda ig is a random variable rather than fixed number. And what the and to test specifically to test the differential expression of one gene between 2 conditions, they may have the lambda ij of the sample j for all the genes I of sample j from the same condition from one same distribution, prior distribution. And if we want to use negative binomial distribution, this prior distribution can be gamma distribution. And also, and so that means it's like a hierarchical model. So with for the samples, even of the same condition, the samples may have different lambda just for one fixed gene. But the lambda, all the lambda of the samples of a same in a same condition, so these lambdas are with a common prior. And this is just a forget about all of the statistical part, the detailed formulations. Just think about by your intuition that if lambda is fixed, there will be a certain variance. But if lambda can be varied, and then lambda controls the variance, so then what will happen? The variance will increase. And if you learn, you have learned some statistics for some computational background students. There is a formula named the total of variance, the theory of total of variance. And kind of if variance is determined by a variable with a distribution, we can compute what the variance is. But the variance is definitely large comparing to if the prior distribution is with a big variance, the variance will be large, but the prior distribution of the variance term will just squeeze, just imagine it will squeeze to one fixed point. And this at the current time, the variance will be the lowest, the true variance. Yeah. And also this is just about the DEC2, the background of the distribution assumption of DEC2. And the other one I want to talk a little bit here is about the RPCAM. Like we have mentioned about RPCAM. So empirically, for RPCAM that is large enough, we can use log normal distribution as the assumption as the null distribution of the RPCAM value through multiple conditions. And if the conditions can be really regarded as the same group as the same population. So that means it's just kind of if you get the RPCAM data and if the data, the genes, all the RPCAM are really large, you just take log and then you can use normal distribution to model it and use t-test. But I will compare the RPCAM using t-test and RPCAM value and versus DEC2 in the hands-on part. Yeah. So, any question about here? Yeah. Of lambda? Yeah. So it's a good question. So basically, the lambda you can give any distribution, prior distribution if it's rational, but you need to test it through the real data. But here, what they use is the prior gamma distribution. First, lambda should be larger than 0, so gamma distribution can be flexible enough. But and also the second, just by my personal understanding is that negative binomial distribution here is convenient to be computed. So they use the lambda, they directly use gamma distribution, which is flexible enough, and also the downstream compute, and then with the prior of the lambda, and with the prior of lambda as a gamma, and with the final distribution from a Poisson lambda, and then the total distribution will be a negative binomial and can be easily to be computed. Yes, the use Bayesian framework. Yeah. Yeah, the user doesn't define the prior distribution of lambda. Yeah, and even in the later case, in the Kansan part, we say there are some things actually the user should be really be noted to that because it will cause some bias. But the user should be able to adjust it, but the software doesn't enable it. But it can be problematic. Later on, we will see that. Yeah. Let's start from the alternative splicing. Yeah. Let's just go back to the main story. Yeah. So there are some. First, I would like to still start from some published study. So let's just start from the definition of just to do a little bit background introduction about the definition of alternative splicing. So here is actually for different organisms, if you note the number of genes of different organisms and the complexity of the organisms, you will see like for some prokaryotes like E. coli, they may have 4,000 genes, but they are just one cell organism, just one cell type. And but for the eukaryotes, human, we have very complicated process. We have longer age. We have the longer lifetime. We have longer lifetime. We have more cell types. We have the tissue structure, and we have different development stage. But the total number of genes in human is just 20,000, not that high comparing to the E. coli. But how human or higher organisms can really reach the complexity of the lifespan of this organism, and also the different functions of different organs or different tissue types of the organism. One way is through alternative splicing. So basically, alternative splicing is one mechanism that sits on top of genetic code and continues to the biological complexity. So it's very important to study because even there are genes and there are genes, and the genes differential gene expression test may tell you, okay, which condition may have significant expression level of the genes. So which condition may have the gene with higher expression or lower expression. But inside of the gene, there are still the eukaryotes genome may still have more flexibility to change just to increase the complexity of the genome code. So here is the definition of the alternative splicing. So in simple words, alternative splicing is alternative splicing is the process where one gene produces more than one type of mRNA. And a more complete definition of the alternative splicing is from Wiki is alternative splicing or differential splicing is a regulatory process during gene expression that results in a single gene coding for multiple proteins. In this process, particular exons of a gene may be included within or excluded from the final processed messenger RNA. So as shown in this figure, so this is the DNA structure of one gene. This figure just illustrates the DNA structure of one gene, and with 3 exons. And triggered by the environment or different development stage, the 3 exons can be formed into just linearly formed into one transcript with all the 3 exons there. And also it can possibly have the exclusion of the middle exon. And this example illustrates that in different cell types, the proportion of the different transcripts product of this gene can be different. Like cell type 1 can have like more percentage of the first transcript, while cell 3 can have the totally absent of the first transcript. And this may really determine the like cell fate and also the increased and also the difference of the cells. And here is just a background about the alternative splicing types. So they're just like the structure, the linear structure of exons. But with this linear structure, there are several possible mechanisms of alternative splicing. So as shown in this figure, the first type is the Casey exon. Which means that this exon can be alternative spliced or not. Can be appeared in one transcript or not. A second is the mutually exclusive exon. These two exons can be just the output. So the final product of this gene are only two transcripts, and two exons are mutually exclusive in the two transcripts. And also another one is named intron retention. That the intron will be in some of the final products, the intron will be present, still be there in the final mature mRNA. And also it can be altered 5' splicing site, altered 3' splicing site, and also some other mechanisms include the altered alternative promoters and also alternative poly A. So these are, and later on we will see there are different regulatory mechanisms may regulate this process, the processes. And also, the deregulation of the splicing process is associated with a variety of disease states and conditions, including cancer. So this go back to this published example. I just found this paper is really very good. It's about mRNA missplicing in disease. It's a Nature Genetics Review paper in 2015. So they first talk about cancer. Let's cover first about cancer. So in cancer, people has observed from the TCGA data and also some other data sets, people has already observed that for the cancer, in the cancer tissue compared to the adjacent normal tissue, they have significantly differentially expressed alternative splicing. Or even so some alternative splicing isoform, they only exist in the cancer tissue. But the detailed mechanism, how this will trigger the progression, drug resistance, metastasis, initiation of cancer, this kind of studies are quite limited. But we just have some hints there. But this paper, I'll go back to this paper. This paper just summarized some really biologically or biomedically some biological evidence have been proven that the alternative splicing, certain alternative splicing or mis-splicing mechanism that is really associated with a certain disease. So for this example, for this familial partial lipodystrophy type 2, is the FPLD2. So for this gene, in the control case, in the normal case, they just have the normal, just the normal alternative splicing of these 3 exons. But for the disease, they may have a mutation in this intron and happen on the 5' splicing site, and may cause the intron retention, and may cause the final protein, the laminin protein, laminin A and C with just a different truncation of this protein. Yeah, and this is one direct evidence of how the alternative splicing associated with disease. And there are some other mechanisms introduced there, and a full list there that show which diseases are associated with which no clearly biologically alternative splicing mechanism. So, and some statistics you need to keep in mind is that more than 90% of human genes express multiple mRNAs, and over 60% of disease-causing mutations disrupt this alternative splicing. And one very interesting case in our lab, what we have done recently is about we annotate, we are trying to study the functional impact of mutations. And we found that there's a trend that the mutations on the same exon, missense mutation on the same exon, may lead to a similar functional impact. That means this is highly associated with alternative splicing. This is only specific in cancer. That's why it's specific in cancer. So, and here, these two figures are very important from ENCODE. The first one just shows the statistics of the average of the number of annotated isoforms per gene and the number of isoforms expressed per gene in two different tissues. So, the x-axis is the number of annotated isoforms per gene for each gene. And for this, and into different tissues, primary cells, cell lines, or tissue samples, they may find by using the RNA-seq data or some array-based experiment, they found the average. The y-axis shows the number of isoforms truly expressed of these genes, truly expressed in each cell type or in different tissue type, or primary cell type or cell lines. So, and you can see that there are some genes with more than 10 or 20 isoforms, and more than just like around more than half of the median value is that half of the isoforms will be expressed in the cell, in a specific cell type. And the second figure shows the x-axis gives the number of annotated isoforms per gene, and the y-axis is the percentage of the percentage of the isoform with maximal percentage in each cell. That means for each gene, probably with 10 isoforms, and we compute the percentage of the percentage of the expression of the exon that with highest abundance in each cell. So the percentage of the expression of the isoform with the highest abundance in that cell. So you can see for this one, just with one, definitely it's just one, just 100% of this data isoform. But with two, you can see that the median value of the isoform with the highest abundance is like around more than 90%. And for the genes with like around 25 alternative splicing isoform, and you can see the isoform with the highest abundance is like around 40% in each cell on median value. So this figure tells us that even though there are highly diverse alternative splicing mechanisms there for some genes, but the isoforms that there may always have some isoforms that dominate in each cell type. They're not averagely or randomly just expressed. So that means there are some regulatory mechanisms that regulate the alternative splicing in each cell of each gene in each cell. So here shows several regulatory mechanisms can regulate the alternative splicing, like RNA binding proteins, small non-coding RNAs, pre-RNA secondary structure, protein-protein complex, and other mRNAs. And this may result, and all this may contribute to the regulation of alternative splicing and may result in the different isoforms. And one specific regulatory mechanism you need to keep in mind is the exonic or intronic splicing enhancer or silencer. So basically, this figure shows how it works. So exonic splicing enhancer is as a definition, exonic means located on exon. Located on exon, and intronic means located on intron. And the enhancer means this may enhance the alternative splicing. And the silencer means this may silence the alternative splicing. And here, this mechanism is that also there are some splicing stimulatory factor. Also, sorry, one thing you need to keep in mind is that the ESS and the ESE and also ISS, ISE, there are some motif on there are with certain sequencing structures. There are some motifs with certain lengths on the DNA, and they can be bound with certain splicing stimulatory factor or splicing inhibitory factors. And once there are, for example, this example, once the ESE, the exonic enhancer is bound with splicing stimulatory factor, they may stimulate the alternative splicing stimulate the exon inclusion. And if they are if the exon splicing silencer is bound with splicing inhibitory factor, so they may inhibit this alternative splicing and may result in just an exon exclusion. There are some different mechanisms. There are also some more mechanisms, and to observe just to quantify the event of alternative splicing or just target it. In the past, there are some technology in the past. One is array-based technology. We have introduced the background of the experiment design of microarray. So it's similar to the microarray. We still design arrays. We design an array to specifically target the alternative splicing event. So comparing to measure gene expression abundance, measuring gene expression abundance, what we need is just the probe just can be unique to a certain transcripts we are interested in, or certain gene we are interested in. But here it's about to target really alternative splicing event. What we need is that we really need, it will be great that if we can get all the exon level information. But sometimes we just know with some prior knowledge, we're really interested in some isoform. And we know that, okay, this isoform are with a unique exon. So we just need to target this exon. But with similar idea, so if we want to fully target all the alternative splicing events in the encoded by one gene, so we need to design the probes. So and for this kind of probe, is that the unit is named probe selection regions, and for this probe selection regions, they are informative enough to, with observation of the expression value of this probe, these regions, these values are informative enough to infer the different abundance of different alternative splicing isoforms. And for each of the regions, we may set like up to four probe pairs, up to 4 probes to measure the expression level of each region, and then we can infer the alternative splicing level with the observed data. Yeah.
Is there any correlation between like the number of the reading frames, size of the reading frames, and alternative splicing for a gene? Because you may be missing exon 1, which would normally contain your start codon, but there's another start codon and an alternatively spliced exon 2.
Mm-hmm.
So is there any evidence of that at all? I was just curious.
Let me think about it. So
this is actually exon array is a technology that is being introduced a couple of years ago, and actually more than 10 years ago, and trying to address alternative splicing, but never came out very useful. And one thing that we still don't quite understand what the reason is when we look at the data, we always see the first exon and the last exon signal is lower. I don't think it's because of the biology. It's more like the technology reason for that. So for this one, the Accumetrics initially put out this product. I mean, there was no sequencing. So they say, okay, you can address the splicing basically by profiling each individual exon individually, and we don't recommend you to compare different exons. Rather, we recommend you to compare one exon across different conditions. So you don't say that the first exon expressed not as much as the second exon, signal is lower, so that your conclusion is that the first exon is lower than the second one. No, that is not the right conclusion, because there are kind of every probe works differently and with different temperatures. You won't get enough of the same level of sensitivity. But the same probe, same exon, if you compare different conditions, they are different. That will be separate issue. But this is actually, the analysis was very complicated, and it never turned out to be very useful, and then later people just moved on, and then sequencing technology came out. So it can be in theory, it can be used on that, but it's not never been really used on. Not much biology came out of this.
Okay. So basically, with using the array-based experiment, we can observe that first the array-based experiment, what we need is we really truly know the isoforms before we design the experiment. If there are some alternative splicing, unknown alternative splicing isoform, some isoform we don't know, we cannot design probes. So, and with the designed probe site and with conduct the experiment, just for this example, we may see that for some probes, they may have high expression. These are two conditions. One condition for these 5 probes, they are with really high expression, and the other are with low on all of the probes. But for this specific probe, we may see the probe or probe site, we may see that the expression level in this condition is really low. That means there are definitely have some alternative splicing event or missing splicing event there. And also another kind of array-based technology design is that splicing junction arrays. So all this figure shows that with known structure of the isoforms to different isoforms, we can always design a certain fix a certain number of probe sites to fully target the alternative splicing event. Just for this example, if the reference is in short form, variation is in long form, we design the probe site A. The probe site A will be the same for also if the total expression level are the same of the 2 isoform. The A will be A will get the same expression rates. This expression the same level of expression level in the two experiment, and the E will be informative to the and the E, C, D, these three probes will be informative to the difference of these 2 isoforms. If the isoforms, the transcripts in the isoform, in the reference isoform will increase the expression level of the E, and the isoform of the variant isoform, the long form, will increase the expression level of C and D. So with this observation, you can just kind of infer, and with this assumption, you can kind of infer the expression level of reference and variant in each of your experimental sample. And also this can be implemented with the existing technology. Yeah, but currently with the sequencing data there, so we don't need we currently don't use this technique. Right.
Sometimes this technology offers higher sensitivity.
Oh, yeah.
So for some of the very low expressed genes and using sequencing based, we have to basically, count dependent on the number of rays mapped across the splicing junctions. But for some lower expressed genes, we may not have enough signals for this technology, and it should be fine. Yeah. But the caveat for this one is you will have to know which splicing isoform you are looking. And so you have to design, for example, for the first one, the intro retention, you need to design 5 probes just to target on this splicing events. So you cannot do something discovery based. It's only that you have to have a very good annotation of the splicing event. If you want to identify novel splicing events, look at it.
So basically, as we have introduced through this course, we can use with the next generation sequencing technology, with the sequencing technology with RNA-seq, and we can just enable our new capability to study the alternative splicing. Just for this example, three exons and 2 isoforms, and the rays just map to 1 exon. It's just it's not informative to determine alternative splicing. It's named constitutive exon, and map to constitutive. And for the rays, that are mapped to the junction region between these two exons and may determine the exon inclusion. That means the expression, the isoforms that with this exon, with the inclusion of this exon. And also the race that with two sides mapped to mapped to one side of the to the right side of this exon and the left side of this exon may suggest the exon exclusion. And in the next part, we will introduce the algorithms to quantify how to quantify the possible algorithms and methods how to quantify the different alternative splicing isoforms in 4 different alternative splicing isoforms and their expression levels from the RNA-seq, just the race data of RNA-seq data. And here is a real example. So we have shown this figure in the first lecture, but and this is on the genome browser. We can see there are several exons, and there are some race that may just map to one exon. But there are also some race mapped to the splicing junctions. That is one part of the race is mapped to one exon, the other is to another exon, to the following exon. But we can see there are some race correspond to possible alternative splicing. Just from this read just map to this exon and this exon, but this read map to this one and this one. So it means the existence of the 2 different transcripts there. Yep. So there are some computational strategies to infer or to study the alternative splicing event from the RNA-seq data. So one kind of method is based on is named isoform-based approach. Just what we will do is based on the race, input race, we will fully reconstruct the transcripts, not all, but the alternative splicing isoforms as much as we can with different assumptions. And one kind of method is namely genomic guided reconstruction, which means with the reference genome information, how to reconstruct the possible isoform or infer possible isoforms from one data set. And the second one is the genome independent reconstruction. That means without the genome, how to reconstruct the possible alternative splicing isoforms from the raw race data, the race data. And there are 2 methods. Namely, for the genome guided reconstruction, there are some methods, but we will introduce cufflinks today. And I will introduce 2 methods, 2 genome independent reconstruction methods. One is named Trinity and second Bridger. And also there are another type of there are another kind of methods that treat this problem in a totally different angle. So it's named the alternative splicing event-based approach. So rather than reconstruct all the isoforms, just focusing this kind of method focuses on the alternative splicing event. That means to infer the percentage of the exon inclusion and exclusion for each exon. And I will introduce the method with mixture of isoforms. This method, and there's another method which is very popular right now, is RMath from Dr. Xing Yixing's group. So let's start from the cufflinks. So basically, the most important thing we want to answer for the alternative splicing, and by using an input RNA-seq data. First is, we want to know what isoforms are in this sample. Second, we want to infer, okay, what's the expression level of the isoforms in this sample? So basically, cufflink is that still like just think about the alignment algorithm we have introduced, like top hat, and then quantification of genes. If there's just one gene level, we can just directly quantify it by the total expression level, like using our total number of rays observed on that gene, like the RPKM. But here the problem is that, so for a gene, we get the total number of rays mapped to that gene body, but those rays may form the different isoform, and the linear, and there is the underlying. First, it's kind of each of the there is a collection of the alternative the isoforms existing in the current sample, And for each of the isoform of that gene, they may have a percentage of the underlying percentage of this isoform in that sample. And what we observed is just a weighted sum of the expression level of all the isoforms there. So here the idea of the cuff link is that from the top hat, from the race mapped to one gene, just from the race mapped to one gene, and by here we use paradigm the race, and how to reconstruct first thing, how to reconstruct all the alternative isoforms that in that data, or infer all the alternative isoforms. And the second is to, just like I mentioned, to quantify the expression level of that. So the first step is just from the top hat data, and we select, and the cuff link pipeline only use the paired and race that are mapped to with spliced fragment alignments, just with the splicing information, just with the splicing mapped to splicing junctions with this information can be informative for the alternative splicing. And the workflow is that continue for the workflow from the FASTQ file and to the band file to the metric file, and we'll select the paired and the paired and race, and that are with the alternative splicing junction information, and do the downstream computation quantification. And with selection of the aligned data, the second step of the cuff link is actually quite straightforward, is to identify the minimum set of incompatible fragments that must have originated from distinct spliced mRNA isoform. So just think about, if you want to solve this question, just to solve the different, just first question, to solve for input data set of the race that mapped to different exons, to the different, and with mapped to different alternative splicing junction region. So you want to reconstruct all the isoforms all the isoforms, or just want to reconstruct the isoforms in the original sample from this data, from the observed data. So there are some possible cases. For example, there is one exon, a second exon, and the possible alternative splicing case could be 4. It's like this one actually 4 minus 1. This one expression, this one is one isoform, and the combination of these two is one isoform. And also there is non-expression. But the problem here is that if we consider it too complicated, it's like we have, if our observation is, we have some of the expression, we have observed the race mapped to the first exon, we have the race mapped to the second exon, and we have race mapped to the junction region. We can say, okay, what is the truth? The truth is the transcript of the first and second exon is definitely there, but we are not sure if the transcripts of the only first exon or the only second exon is there. We're not sure. But here, so if you think about if the number of exons just increase, if there are too many alternative splicing isoforms we enable there, and there will be more uncertainty. So what a cuff link did here is that the cuff link wants to find a set of isoforms, just the smallest set of isoforms that can explain all the race we have observed. So for example, if we just observed, for that case, we just observed the link of, for 2 exon case, we just observed the exons, the race mapped to the junction of these 2 exons. The final result of cuff link will be just one isoform. And here the purpose of this step is just to identify the race that maps the race that cannot be explained, can definitely be explained by the can definitely be explained by the distinct this step is just to identify the race that definitely are not from the same isoform. and then they may connect. This is the most important part I think, is they generate an overlap graph to link the rays. So for each of the rays, if these rays are if two rays are overlapped, they may form one graph. They will be linked on the graph, and you know express the side of the direction of the sequence of the MRA. So this one will be a acyclic graph. And with this one, you will definitely, and for all the rays, you will construct a graph. And over the graph, you will see, and the graph may have some characteristics. One characteristic is that if the graph, and there are some fragments on the graph are not compatible. That means in graph theory, this graph you may need different paths to cover this graph. It may need how to say that means this graph and so with construct the graph of those rays, and for some of the rays, and let's stop.
Do you want me to?
No, I think I'm fine. Just give me a break.
Okay.
Let's stop. Yeah, thank you. Yeah, sorry.
Take a 5 minutes break.
Yeah, take 5 minutes break.